We introduced SceneLinker, a novel framework that generates compositional 3D scenes via semantic scene graphs from RGB sequences. Recently, mixed reality systems such as Meta's SceneScript and Apple's Room Plan have demonstrated how understanding user environments and generating 3D scenes can enable spatial awareness and content creation in AR/VR. Then what are the key elements required to create interactive 3D scenes for users in AR/VR environments? In this work, we focus on two essential components. First, we aim to understand compositional 3D spaces through a simple and compact representation. Second, we focus on generating object-level 3D meshes that accurately align with the real-world layout. To address the first point, we adopt a 3D scene graph as our core representation. Existing research on 3D scene graphs can generally be categorized into two main approaches. The first is a hierarchical approach, which organizes scenes at the room level to provide a structured understanding of large-scale environments. The second is a pairwise approach, which focuses on predicting relationships between objects within a single room. Among them, recent pairwise scene graph approaches have emerged as a key tool for representing user-object and object relationships in AR/VR environments, enabling applications such as remote collaboration and agent-based interaction. However, these existing approaches still have notable limitations. Most state-of-the-art methods primarily focus on detecting multiple objects, which restricts their ability to reason about relationships between objects. Meanwhile, to generate a 3D virtual scene from a graph-compressed representation of space, we adopt a graph-to-3D approach. Intuitively, this means taking a scene graph as input and synthesizing a 3D virtual environment. Recently, diffusion-based methods have achieved state-of-the-art performance on this task by generating diverse shapes and synthesizing high-quality 3D meshes. However, they still require around a minute to infer a single scene and mainly focus on generating diverse shapes rather than producing 3D scenes that are consistent with the input graph and its context. To address these limitations, we propose SceneLinker, which generates 3D virtual scenes from RGB sequences by predicting a relationship-consistent 3D scene graph. To improve the robustness of scene graph prediction, we design a cross-check feature attention mechanism that performs adaptive, node-wise feature refinement. Moreover, for 3D scene generation, we introduce a graph-VAE that jointly infers shape and layout, strengthening scene-level consistency and achieving performance beyond prior state-of-the-art methods. Our method consists of two main steps: predicting a 3D scene graph and generating a 3D virtual scene. First, given an input image sequences, we estimate 3D entities using the SG Fusion module, which combines visual SLAM with 2D entity prediction. Each estimated 3D entity is associated with an oriented bounding box, 3D points, and image features. To encode these features, we extract image embeddings using ResNet and point embeddings using PointNet, and then concatenate the two representations. Next, we construct a neighbor graph among 3D entities using a bounding box collision detection strategy. Entities that overlap or are within close proximity are connected as neighbors. Each node contains point and image features, along with bounding box attributes. For each edge, we compute a relative pose descriptor, which encodes the relationship between two bounding boxes by measuring the relative minimum and maximum offsets. In this stage, we employ a graph convolutional network to propagate and update object features at the graph level. In particular, to capture richer contextual information between objects and predicates, we introduce an attention-based mechanism that cross-checks relational cues from neighboring entities. The graph network updates each object node by exchanging features with its neighbors through two message passing layers. However, instead of using simple message passing, we design an attention mechanism called cross-check feature attention, which enables more robust and stable message delivery across edges. As predictions for nodes and edges are repeatedly produced over time, it is crucial to accumulate them stably and consistently, merge observations that correspond to the same object. To achieve this, our system adopts a weighted running average scheme, which updates both the probability predictions and their confidence at each time step. As a result, we can integrate per-frame graph predictions into consistent global scene graph. Now, to convert this compact scene graph back into a 3D scene, we need a shape prior. We augment each graph node by attaching a pre-trained 3D shape code based on deep SDF, conditioned on the predicted object class. As a result, each node contains the shape code of its predicted class, along with its bounding box and class information, while each edge retains the relationship information. Inspired by common scenes, we further enrich the scene graph representation by adding text features extracted with a clip encoder to the original node and edge features. In addition, we parameterize each bounding box and transform it through a map, then concatenate it with the node features to obtain a richer and more expressive graph representation. Then the extended scene graph is fed into a graph-VAE to generate a 3D scene. To synthesize a 3D scene with a layout that is consistent with the graph context, we design a joint shape and layout block that jointly learns shape and layout representations. The JSL block consists of two stages. First, we fuse shape and layout features into a unified representation using a GCN-based fused network. Next, we further refine the features with a GCN-based layout-centric network, which takes the layout features together with the fused representation and enhances layout consistent structure. After passing through an encoder composed of two JSL blocks, we decode shape and layout via separate decoders and combine them to synthesize the final 3D scene. For training, we follow the standard VAE objective by combining a reconstruction loss with the KL divergence term. For experiments, we use real-world datasets, including 3R-scan and 3D-SSG, to evaluate scene graph prediction. For evaluating 3D scene generation, we use 3D front and SG front. For evaluating scene graph prediction, we follow prior work and report top K accuracy using recall and mean recall. Specifically, we evaluate relationship prediction over the entire scene graph, object classification, and triplet prediction that jointly considers two objects and their relationship. For 3D scene generation, we use the scene graph consistency metric to measure the accuracy of the predicted relationship set in the generated 3D layout. First, we present quantitative results on 3D scene graph prediction. Our model outperforms prior state-of-the-art methods, achieving particularly strong improvements in triplet prediction, where object pairs and their relationship are jointly considered. This indicates that our cross-check mechanism on attention weights between neighboring nodes enables more precise modeling of semantic connectivity between objects during relationship inference. Next, we show the results on 3D scene generation. Our method achieves comparable or better performance than prior approaches under the easy setting, and under the hard setting, it outperforms the previous state-of-the-art by 6.5% and 14.5%. Notably, we outperform MMG Dreamer, even when it leverages both text and image inputs. These results suggest that our proposed JSL module, particularly its layout-focused refinement strategy, has effectively improved scene-level consistency in challenging cases. Also, we compare inference runtime between prior methods and our approach. Diffusion-based models, including Common Scenes, EchoScene, and MMG Dreamer, require between 26 seconds and nearly 1 minute per scene. In contrast, our method achieves a runtime of only 1.03 seconds. Since responsiveness is critical in AR/VR environments, these results demonstrate that our design choice of adopting a VAE-based architecture is highly effective for practical interactive applications. Next, we show qualitative results. The scene graph is shown on the left, and the corresponding generated 3D scene is displayed on the right. For example, in scenarios with symmetrical relationships, our approach produces scenes that better satisfy the target relationships compared to prior methods. As another example, even in scenes with closely spaced relationships, our model generates a coherent layout in 3D scene that consistently satisfies each target relationship. Next, we show the real-world environment, the predicted scene graph, and the generated 3D scene. In summary, SceneLinker predicts a relationship-consistent 3D scene graph and generates structured 3D scenes from RGB sequences. Our cross-check attention in graph-VAE with the JSL block enables state-of-the-art results. One limitation is that inaccurate early bounding box estimation can lead to incorrect scene generation. For more details and additional results, please refer to our paper. Thank you.